Gosh, good morning, ladies and gentlemen. It's been 2 or 3 years since I've been here last giving a talk, and it's nice to be back. I want to turn the clock a little bit back now to something a bit maybe more fundamental in terms of permeability. I'm going to talk to you on the effects of sourcing, compaction, cementation on porosity and permeability. And what we're going to be doing is looking at it from the point of view of a theoretical description, and some numerical modeling, some experimental data, which we made in the laboratory at very high accuracies, and finally, if we have some time, process modeling. And what I want to do is to look at some porosity, some permeability, of course, because that's the title of this session, the fractal dimension of the rock, and the specific surface area, although those last two only to a small extent. We have in rocks a complex system, and it's already been alluded to by Scott that we perhaps look forward to seeing a nice bead pack sort of solution. I'm going to show you information today that actually tells you that we can actually simplify most rocks to that situation and not suffer from it. So this is about inferring the complex from understanding the simple. So I wanted to start, with a conceptual model. This is the conceptual model. This is how porosity in a 2B size pack will change depending upon the volume fraction of the grain. So on the bottom here we have the volume fraction of the grains, and you can see here we start off on this side with a lot of big ones, a lot of small ones on this side, and there's some sort of gradational behavior in the middle. And actually, if you look at the porosity from that situation, you get a curve that looks a little bit like this, where you have the porosity of the coarse grains on this side, the porosity of the fine grains on this side, and some ideal packing of the two of them, which is some porosity that is lower than that. And of course, that has an effect on the permeability as well. So that's the concept, and it includes two processes. It includes a process of interstitiation, where the small grains are distributed within the pore space between the large grains, and a replacement process where the large grains replace an amount of small grains, as it were. The critical porosity and permeability occur when those balance. So looking at this in a little bit more detail, these top two diagrams show the interstitiation process, where you have the space between the large grains being filled by small grains, and therefore reducing the porosity. And the second two down here, C and D, show the process of the replacement process, where you end up actually having to cut out a certain amount of small grains in order that a large grain can go in its place. Now, of course, when you do that, then you're cutting out both solid material and porosity to replace it with solid material, so you're reducing the porosity. But you're not doing it in the same sort of efficiency as just by adding grains into pore space. So the two processes are mathematically different. And also, when you do this process of replacing with a large grain a whole load of small grains, you have to be very careful not to cut any of the small grains in bits, but to actually nestle them to the side in what we call a non-cutting replacement process, where this will be a cutting replacement process. And I make the distinction that way because I want to show you now the mathematics that is behind that conceptual model. Mathematics is actually really quite simple, and it's actually quite amazing in some ways. So here we have a graph of, on the x-axis, fraction of fine grains, and on the y-axis, porosity. This here is the interstitiation process, and this is the replacement processes. The dashed line is for cutting of fine grains, but the non-cutting line, which is the one that happens in reality, is the red line. So these two lines, the blue line and the red line, represent what the porosity would be in a rock that is made out of two types of grain size. So that's very nice, the mathematics isn't so very complex, as it were. It doesn't contain any differentials or integrations or whatever. But if you look at it carefully, it doesn't contain anything about grain shape. It doesn't contain anything about absolute grain size. That's not because it only works for little spherical particles of a certain size. It means it works for any grain shape and any grain size. It's independent of both grain shape and grain size. All it does require is you to know what the end member porosities are. So if your end member porosity up here was a pack of cylindrical grains, then the mathematics would work just as well. If this one over here, the fine grains, were all represented by rhomboids, then that mixture of rhomboids and cylinders would follow the same mathematics as here. So we have something that's really quite general, but it's for two grain sizes. Later on in the talk, I'm going to more generalize still and go to greater numbers of grain sizes. But for the time being, we have some mathematics, we want to test it. And so we have this challenge in the laboratory of trying to actually measure the porosity and the permeability as accurately as possible to be able to get this mathematics tested. And the only thing you can do to actually really have high quality measurements in the laboratory is return to your roots and to try and make things physically, from a physics point of view, as simple as possible and as accurate as possible. So we used a Perspex cell that looks like this. We have some resistivity measurements which I'm not showing you today. And basically it is just not a pump-driven, but a gravity-driven system that measures the volume of fluid flow gravimetrically with a balance, because that's the most accurate way of doing it. And we were able to get porosity uncertainties down to about just over 4%, and permeability uncertainties down to just about 5%. It's the permeability one that matters here. We can actually get porosity uncertainties down to about 4% using standard sorts of measurements. The trick was to be able to make both measurements with accuracy in the same cell at the same time with the same compaction. And so although I'm showing a table now, I'm not going to dwell on it too much. This is just to show you that we used a number of different glass beads of different sizes, where the sizes were measured accurately with the laser. We've had a calculated modal pore diameter using the Glover and Walker method, a calculated modal pore for diameter using the Glover and Derry method, a number of mercury and helium measurements, and a measured porosity in the experimental cell to check it all. So everything is actually certainly defined. Over here we have calculated cementation exponential formation factor, a measured permeability, and the predicted permeability from the RGPZ equation. I didn't have a chance to ask Scott a question because there were so many other good quality questions. We use the RGPZ equation because the Kozenyi-Kármán equation is known to overestimate permeability because it doesn't take account of dead-end pores and pore throat paths. And this is usually accounted for by using tortuosity as a sort of a variable fitting exponent, as it were. So that's the reason why we've got our GPZ up here. So if we look at the data, then we get this for all the mixtures of all of the samples we have. And they're glass beads up here, and they're Ottawa sand and fine sand, and glass beads and Ottawa sand down here. You can see the experimental data is points with error bars, and you can see that it actually follows the mathematics really very well indeed. So we were very pleased with this when we published the data 2 years ago. Of course, it matters very much whether or not you have a good compacted, not compacted in terms of pressure, but you've settled the system right. So if I just put up this slide, you can see the effect of settling. You end up having to agitate this mixture, any mixture you have, really quite a lot, because if you measure the porosities when they're initially mixed together, they look like this, but after a certain amount of agitation, after a second shaking, you find they get closer and closer to the experimental values, which is what you think you might need. Okay. So far we've talked on a really quite fundamental level about mathematics that describes just 2 grain sizes and concentrates on porosity. Now we're going to start looking at the permeability that is associated with that, the experiment and the calculated permeabilities. So here are the equations that we've used. It amounts to 11 models of permeability altogether. The top 3 are just geometrical mixes of cubic, arithmetic, harmonic, or geometrical. The bottom 2 are the Kozeny-Kármán model and the RGPZ model. Each of those models requires to have a grain size average. And that grain size average, of course, can be an arithmetic average, a geometric average, a harmonic average, or actually a cubic average as we've used here as well. So the question is which one of those would work well, and it's pretty well attested or expected that the geometric one will, because it's the geometric one that we all use when making calculations that way. So if I put those on a graph together with the experimental data and using the porosities from the porosity model that we have, then we get this graph here. This graph here, the top and the bottom, is the same data, except that in the top one we have it on a linear scale, and in the bottom one I've turned it into a log scale, if you prefer to look at it that way. And we have the experimental data together with its error bars, and also we have all of these models. And it's really difficult for you to see by just looking at this diagram perhaps what is best, but actually the best model is the RGPZ geometric bit, which is this green line here that goes through this data. Now this is the data for only one mix. I wanted to show it to you as one mix at a large scale so you can see the detail in it. Now what I want to do is to give you all of the data, and this is what all the data looks like, so you can see that the one I showed you earlier isn't just happenstance a really good fit, they all are a pretty damn good fit to the RGPZ geometric model. It must be said that the Kozeny-Kármán geometric mix model is also fairly good, just not quite as good. Right. So I said to you that you might say to me, let's say 2 grain sizes isn't going to be interesting because we know real rocks contain many more grain sizes than 2 grain sizes. So we've actually extended the model to 3 grain sizes and 4 grain sizes. And I'm going to show you a couple of very, very recent bits of modeling that takes that into account. So this is a 3 grain size solution, and here we have the porosity on this z-axis, and the x-axis, or the x and the y-axis if you like, are the fraction of grains which are smaller than, or they're finer than, the coarsest grain in the 3 grain mixture, but they're the different sizes of them. And you find that on the planes, you get the same behavior as we had before, and any crossing point that is diagonal across here looks rather similar as well. But interestingly, the porosity isn't reducing very much. In fact, there are situations where the porosity doesn't reduce at all, but it's slightly bigger. So what this is telling us is, mathematically, when we have more than 2 grains mixing together, the 3rd grain, the 4th grain size being added in, makes little difference compared to that first 2 grain mixture. So if we look at this same data from the point of view of a projection, if you like, here we have the fraction of fine grains B in this direction, the fraction of fine grains A in this direction, and the colours representing porosity. You can see from these sectional lines here, the blue one is this line, the red one is this graph here, and the green one that you perhaps can't see very well, which goes diagonally from corner to corner, is this one over here. Shows you that we're getting the same sort of type of behaviour, but actually the difference between the red and the green curves and the red and the blue curves here, which actually is the difference between a 2-grain mixture and a 3-grain mixture, it's moving the critical porosity, but it's not making it much smaller or much larger. I must say that was quite a surprise to me. However, it must be said that if you are introducing a third phase which is very, very low porosity, such as a micrite, then that, of course, is going to control your situation. You might expect a mixture of 3 grains to be represented as a ternary diagram. The reason it's not a ternary diagram is actually it depends upon the introduction of each of the grain sizes. And so this is effectively 4 ternary diagrams plotted on top of each other because it depends, it matters which grains you add in which order. And because it depends upon which grains you add in which order, then we did some process modelling. This is the process modelling that we were doing, and I like to think of it as Tetris for petrophysicists, because this is a 2-dimensional example to show you how it was done. We did it in 3 dimensions because it's only valid to do in 3 dimensions. We take a box, basically, and introduce at random a grain size. At least it's chosen from a distribution of grain sizes that we define, and we let it settle somewhere on the substrate according to where the energy is lowest, and then we do it again and again until we build up the whole model. And that's done in 3 dimensions. And once we've got that model, we can do a whole load of tests on it about fractal dimension and about surface area, specific surface area, about porosity and about permeability. But we can also take this model, this 3-dimensional model, and we can make it more compact by pressurizing it numerically, or we can grow cement on the surfaces of the grains to see what cement is going to do. And I'm going to show you now the results of that data in 3 dimensions. So we have here an example of 3 models, V1, V4 and V7, and the models are shown up here in this table. And as you can see, V1 is just a single grain size, V2 has 2 grain sizes, and so on. So V7 here has 7 grain sizes making up this model. And the model is created in that depositional process that I showed you earlier. When we do that, we find that we have, with decreasing sorting, fractal dimensions approximately staying constant, the specific surface area increasing, and this is the porosity slightly decreasing here. We also have the permeability decreasing with a decreasing sorting. Now, that's not a surprise. We all know that is. We see it every day. You know, the more sorted our sandstone or whatever it is, the higher the permeability, and the worse sorted it is, the lower the permeability. I want you to see here that the permeability is on a linear scale in this particular diagram, because now I'm going to show you the same thing as a function of compaction and as a function of cementation. And in those 2 diagrams, the permeability will be on a log scale because it's a bigger change. So if we do it with compaction, and these are again 3 particular examples of what we call a compaction coefficient. Basically, it's just a linear fractional compaction in each of these cases. So CP equals 0 means no compaction, and this is a 12% compaction, and this is a 24% compaction in the direction in which we're making the measurements. You can see that now as the compaction increases, we have a decrease in all the fractal dimensions, rather large increase in the specific surface area, a large decrease in porosity, but also a very large decrease in permeability. So compaction matters. That was matters more than sorting. So if your original depositional rock has bad sorting, it's not necessarily a bad thing. What really matters is what sort of compaction it undergoes afterwards, or diagenesis if you're looking at a limestone. So let's look at cementation in the same way. Again, now we have three different thicknesses of cementation going on to our models. The models are created in the same way as before. This is a model, as was the one for compaction, which has, I think, three different sizes, maybe four different sizes of grains. And we can see, once again, the fractal dimensions decrease in size, the specific surface area increases, and the porosity decreases. And of course, the permeability is going to decrease. And again, this is on a log scale. The permeability is decreasing by many orders of magnitude as a function of that cementation. So, just in terms of summary, I'd just like to say that theoretical methods do exist for 2 to n grain size phases. And surprisingly, the equations are independent of absolute grain size and specifically grain shape, which is very useful indeed. The theory agrees very well with the measurements that we've made. We've tried to make the measurements as high quality as possible, and the prediction of porosity and permeability is possible if you look and use the RGPZ equation with a mean grain size given by a geometric average, a geometric mean. When you look at order mattering, then process modeling can account for the effects of sorting and compaction and cementation, and by definition, dissolution as well. I haven't shown you the dissolution slides here today. And finally, prediction of porosity and permeability, fractal dimension, and specific surface area are all possible using these types of measurements. So just in the same way as one might use, say, a synthetic seismogram to understand better your seismic data, you might actually use modeling like this to understand a little bit more about the microstructure of the rocks that you deal with. Anyway, thank you very much for listening to me today. It's good to be back. And if you have any questions, I'd be glad to take them.